Yeah, sure.
Okay, so we are starting to record. Okay, so welcome everyone to this week's AI seminar. Today we are very fortunate to have Professor Snigdha Chaturvedi from University of North Carolina, Chapel Hill. So Snigdha specializes in natural language processing with an emphasis on narrative-like and socially aware understanding, summarization, and generation of language. Previously, before UNC, she was assistant professor at UC Santa Cruz and also a postdoc fellow with Dan Ross and also UPenn at at UIUC and UPenn. So Snigdha earned her PhD in computer science from University of Maryland in 2016, where she worked with Howard Domain 3. So today, Snigdha is going to talk about natural language generation with planning.
Thanks, Mahal, for the introduction, and welcome everyone. So today I'll be talking about natural language generation with planning. You might have heard this quote, think before you speak. And there's even some research showing that babies think before they speak. Yet modern natural language processing methods and natural language generation methods do not. This wasn't always the case. In the pre-deep learning era, the natural language generation models were essentially a pipeline system, and there were explicit planning stages where before they generated any piece of text, they would plan the content and the structure of the text, and then they would generate. With the advent of deep learning methods, there was a push for more encoder-decoder style of models where the models directly took the input and produced the output. And they don't have this explicit planning stage. In this talk, I'm going to discuss methods which are deep learning methods, but they plan before they generate. In particular, I'm going to talk about these three pieces of work. The first one is about data to text generation with auto-generated or machine-generated plans. This was published in ACL 20. The next piece of work is about multi-document summarization, also with auto-generated plans. And lastly, I'll talk about story generation with human-provided plans. This was published in EMNLP 20. So at any point in this talk, if you have a question, feel free to type it in the chat or just unmute yourself and speak up. I cannot see my chat, so unless somebody interrupts me, I won't know that there's a question. And Muha has kindly agreed to monitor the chat window for me. Okay, so let's start with the first piece that is about data to text generation with self-generated plans. This work was published in ACL 20 and was titled Bridging the Structural Gap Between Encoding and Decoding for Data to Text Generation. This work was led by my student Chao Zhao, and who's currently at UNC. And it was done in collaboration with Marilyn Walker at UC Santa Cruz. So the problem here is as follows. You are given a graph that contains some information. Like in this case, I'm showing you a graph on the left. It contains information about Mona Lisa, the painting, where it's located, who visited it, who painted it, and so on and so forth. And the task is to convert the information contained in this graph into natural language text, such as interested in Mona Lisa, it's on display at the Louvre Museum in Paris. So why is this an important task? If you're a computer scientist, you very well know that computers don't work very well with natural language text. Most of the data that's stored in computers, which includes web data and all sorts of soft data, is stored in structured format, like a graph or a table. And this is because this format is very easy for computers to understand and to process. But tables and graphs are not the easiest things to understand for lay people. Lay people understand text. And so if you want to convey the information that is stored in structured computers to lay people, you need to convert this data this information into natural language text. And that's why this problem is important. So the key challenge in this task is that there's a structural gap between the input, which is a graph, and the output, which is text. And so it's sequential in nature. We read text from left to right, and so it's sequential. And in this paper, we bridge this structural gap by planning. So before I describe what we did, let's think about how you would solve the problem in today's date without planning. If you were to not plan, you would simply take an encoder-decoder architecture like LSTM or transformer. Here I'm using LSTM for illustration. So you would take the input data, feed it into LSTM encoder. It will go into an LSTM decoder, and then the decoder will output the text that you want. But in this process, when you are feeding the input data to the encoder, the input needs to be sequentialized, which can be an unnatural process because this is a graph, and it's not very obvious how it should be converted to a sequence. And in order to handle this problem, we insert a planner. So this is like a very rough overview of what we do. We essentially insert a planner between the input and the encoder-decoder model. So let me talk about the model. So the input to the model is a set of unordered triples of subject, predicate, and object. And we then utilize a graph convolutional network to encode the graph and get the hidden state representations for each node in the graph. So once you have the hidden representation for each node in the graph, in the next step, we utilize a planner module to reorder the input nodes into another order based on these hidden states. I'll describe how we do this planning later on, but this is what we do. And then once you have a nice order for the input, once you have a nice order, a reordered input, which is determined by the planner, then in the next step, we can utilize any sequential encoder, such as an LSTM or a transformer, to encode these nodes. And then in this paper, we used LSTM, but you can use any sequential encoder. And then we use a decoder to output the actual text. So this is the architecture of our first model, which we call Plan Enc. I've written model 1 because there are 2 models. But as I mentioned before, we want to further incorporate the structural information that is present in the input. And for that, we also additionally use the hidden representations of the graph encoder. And so we basically get the hidden representations of the graph, and then we concatenate them with the representations that we get from the encoder, and then we feed them to the decoder. So this is the dual enc model, which is our second model. So I've described 2 models. The first model was a plan encoder in which plan enc model in which we took the planned input order, reordered inputs, and we fed them to an encoder-decoder model. And then we have the dual enc model, which is the second model, which additionally considers the hidden representations from the graph encoder. So in this setup, I did not describe how the neural planning module works. I only described how that there is a model, and now I'm going to describe the module, the planning module. So for the planning, like, you can consider the planning process as a classification problem. And the task is that at any point you have to choose a predicate to express. And then once you have chosen one predicate or one node, then you consider the rest of the nodes and choose the second one, and so on. So this is the high-level idea behind the planning component. We take the nodes, X's, we convert them to their hidden representations using a GCN, and then we pick a node to express. So this, for example, we chose assembly here, and this is done using a simple classification module. Once we have chosen assembly as the node to be the first node, then we mark it with a special token and we redo this process. So we again consider all nodes, we consider the their hidden representations, and then we choose a node from the remaining nodes. Let's say we chose capital, we mark capital as something that we have visited, and then we keep repeating this process until we have chosen all the nodes. And so by doing this process, you can see how we have converted the graph into, we have obtained a serialized plan from the graph where we have the order in which we want to mention the predicates, like we want to mention assembly, then capital, then successor, and then finally manufacturer. So this is a high-level description of our model. And now I'm going to describe our results. So we experimented with the WebNLG datasets. It's a very standard dataset for data to text generation problem. The input is an RDF graph like the one shown on the left top, and the output is the textual description of the graph as shown on the bottom. There are about 9,000 distinct inputs and about 25,000 data to text pairs. The test set consists of two parts. The first part is a scene set. And in this, in the scene set, there are the domain of the instances are the same as domain of training instances. And then there is an unseen test set. And in the unseen test set, the domain of instances are new. They are from 5 domains that are not seen during training. So, so here are the results for generation. I'm showing the blue score here, and various bars represent various models, baseline models that we experimented with. So in this case, and I'm reporting the first set of bars represent the results on the scene part of the test set. The second set of bars represent performance on the unseen part of the test set. And the last set of bars is a combined measure on the entire test set. So we compare with the following baseline. The first is a statistical machine translation-based baseline. The next 3 green bars represent neural sequence-to-sequence models. The next 3 blue bars also represent neural models, but these are like pipeline methods, but their pipeline is different from ours. And in the purple bars, I'm showing you the performance of our 2 models, planning and dueling. So we can see from this graph that, from the chart, that our models, the planning and the dueling model, are outperforming, the baselines. Then we also conducted human evaluation, and we found that dual-link model actually performs better than the planning model. So in the human evaluation, we compared dual-link with various baselines, and we asked human judges to compare outputs of dual-link and a second model, which a baseline model, and the humans were asked to judge which of the 2 outputs is better. They were asked to judge the quality based on coverage, which is how much of the input information does the text cover. Faithfulness, how faithful is the text to the input information? Is it hallucinating and stuff? Fluency of the text, and then also like an overall measure. I'm sorry, the slides are advancing on their own. Maybe there's a setting I needed to change. Each of the bars represent various baselines. A positive score means that the baseline was better than dual-link, and a negative score means that the baseline was judged to be poorer than the dual-link model. We can see that dual-link is outperforming all baselines, which includes planning. And in fact, dual-link is outperforming planning, and we hypothesize that this is because dual-link is the model that has additional direct access to the structural information of the graph. And so probably it's doing better in terms of coverage, faithfulness, and fluency because it can incorporate the structure also. Lastly, I also want to show some generated examples. So in this slide, I'm showing examples of text generated by various models for one given input. The input is shown on the top row. It consists of 6 triples. The last row shows the reference or the human written answer for this input. The second and the third row represent 2 baseline models, Melbourne and Step by Step. The fourth and the fifth rows represent the planning and the dual-link model. I'm highlighting mistakes in different colors. So purple color represents missing information, red color represents unfaithful information, and blue color represents influent parts of each text. And so, for example, if you look at the row in planning, I'm highlighting that Buzz Aldrin is missing in this text description. It was there in the input, but it is not there in the text description. And so this is a mistake. We can see that the various models are making different types of mistakes, but Dual-Link is able to overcome all of these problems and generate good quality text. Are there any questions so far?
Yeah, actually, I have a quick question, Snigdha.
Uh-huh.
So my understanding is that the planner, the serializer first serializes every node. Then
Yes.
based on the complete plan, you do the generation,
Yes.
right? Have you tried any interleaving method, which means that you generate, you select one node, and based on this node, you generate, a part of the utterance. Then based on the utterance and the previous node, you select the next node. Those kind of like interleaving.
So can you repeat the last part? Like you select the first node and then what?
Oh, this is more like an interleaving. So you don't generate the entire plan, but generate every node in the plan, then the corresponding utterance, then the next node.
No, so we did not try that, but that's a good idea. Like you might want to, so in this case, what we do is we select the entire plan, like we want to mention assembly, capital, successor, manufacturer, and then we generate the text. And the question is that maybe we choose assembly, generate the corresponding text, then choose capital, then generate the corresponding text. And that might actually change the plan. We did not try that. I think the tricky part there is incorporating, like understanding what the model has generated, because as we know, these models are not very good at understanding text. I think that right now these models are not like super fluent, but as we get better models, I think that even like as a human, if you know all you want to say, then you might do a better job than saying something and then thinking, then saying something else. Like the text, the generated text could be more fluent if you have the entire plan at hand. But that's just my hypothesis. We haven't experimented with this, and that's an interesting direction to follow. Thanks.
Okay. Yeah, thanks.
Are there any other questions? If not, then I'll move ahead. So here are the key takeaways. The first takeaway is that we showed that for a problem like this, for data to text generation, dual encoding is important, which basically means that we need to incorporate the textual information as well as the structural information of the data in order to generate accurate and faithful text. The second takeaway, which is the gist of this entire talk, is that you need to plan. The order of the input should be carefully determined for better generation quality. And we used this idea, the second bullet, we used this idea of planning, of reordering input for for the second project as well, which I'm going to describe, which is about multi-document summarization with self-generated plans. So this work was published in Findings of ACL 22 in the paper titled Read Top News First, a document reordering approach for multi-document news summarization. This was done by my students Chao Zhao, Teng Hao Huang, and Somnath Basuroy Chaudhary. And it was done in collaboration with folks at Amazon, Muthu and Kathy McKeown. So the problem here is multi-document summarization. In case you are not familiar with the problem, it's a standard problem in an NLP. In case you're not familiar with the problem, the input is a set of documents like news articles from various news companies, news agencies about an event. And then the goal is to generate one paragraph summary of all of these articles. So the challenge here is to combine information, is not to just like summarize one document, but to combine information from multiple documents and then summarize them. So when working on multi-document summarization, a very popular way that has been quite successful so far is to reformulate the problem as a single document summarization problem. So what people do is they concatenate the documents one after the other and form a meta document, a meta concatenated document. And that is fed into a single document summarization module, and the summarization module creates the summary. So this has been like fairly successful. It has been giving quite good results, but many times the salient information in news articles appears at the beginning of the document. And therefore many summarization systems also pay more attention to the beginning of the document. And when concatenating document into a single meta document, some documents contain more salient information than others, but they could be appended at the very end, and the summarization module will not pay attention to those documents. And so therefore, it's important to concatenate these documents in a reasonable order. So for example, if you have 3 documents, document 1, 2, and 3, and the third document is most important, followed by document 1 and document 2, then you want to place the document 3 first in the concatenated document, followed by document 1 and then document 2, so that the concatenated meta document has more important information or more salient information in the beginning. And then you can use a standard summarization module to create the summary. So I want to mention upfront that in this paper, the key contribution is on the planning or the document reordering side, and there's not a technical novelty on the summarization module side. We are using standard summarization models in order to do the summarization. So motivated by this idea, and motivated by our success in the previous problem, where we showed that planning can improve generation quality, we decided to explore the possibility of reordering input documents before concatenating them into a meta document and seeing if that leads to better results. So we explored 2 possible document reordering methods, a supervised method and an unsupervised method. In the supervised method, we wanted to train a BERT model or any other model to identify the saliency of a document. Now, for training this model, we define saliency of a document as how similar the document is to the gold summary. So basically, the idea here, have access to gold summaries. We see how much overlap there is between a document and the gold summary. We'll look at the Rouge score. That is the importance score. And then we use BERT as the importance learning module. Our learning objective is to minimize the KL divergence between the predicted importance scores and the gold importance scores, which are determined using the gold summary. So in the supervised setting, we train this BERT model, we have access to the gold summaries. When we are in unsupervised setting, we don't have gold summaries. And so we approximate the gold summary by considering the top 3 sentences of every document and concatenating them and treating that as the gold summary, and then following the same procedure. We also experimented with using other ways of modeling document importance like length, but we found that this was the most useful way of measuring importance. Okay, so this is our planning module. This is basically our document reordering method. And now I'm going to describe if in our experiments, which investigate whether reordering the documents can lead to better summaries or not. So we experimented with the multi-news dataset, which is a standard multi-document news summarization dataset. We measure the summarization quality using root score. A higher score is better. And in this case, I'm showing the root scores with randomly concatenated input documents. So we are not using our planner at all here. We experimented with 3 types of summarization modules. The first is PACSUM, which is an unsupervised model, PRESUM, which is a supervised model, and then PRESUM _ CNN Daily Mail, which indicates a supervised model that was pre-trained on CNN Daily Mail, which is a standard news summarization data set. I'm showing Rouge 1, Rouge 2, and Rouge L. So here we see that if you don't do any planning, what would be the Rouge score of these various models in supervised and unsupervised settings? As expected, you can see that the unsupervised scores are lower than supervised scores. And you can also see that the purple bar is slightly taller than the blue bar because pre-training gives a little extra boost to the performance. Now we use our document reordering approach to reorder the document before we feed those concatenated meta document into these models. And the darker shade of each color shows the performance with reordering. So for example, on the left, the leftmost bar is PACSUM, or the unsupervised model with randomly concatenated documents, and the darker green is the same model with reordered documents before concatenation. And we see that we get a boost of 0.55 for Rouge 1. Similarly, you can look at all these bars. You see that the darker color is taller than the lighter color, indicating that if you reorder the documents, it leads to better Rouge scores. Are there any questions that I can answer at this point?
Yes, Snigdha, I have another question.
Uh-huh.
So I've been very interested in biases in multi-document summarization. So I can think about 2 which is relevant to this work. So one is the positional bias, which matters about, what's the order of the document you send into the summarizer. Definitely your work can address this kind of bias. And the other kind of bias, I would maybe call it a frequency bias. If we think about, we summarize multiple reviews into a meta review, suppose, that it's possible that over there, let's say there's one single probably negative review, which is the most infrequent one, but that's very important. So when you summarize into a meta review, maybe it's likely that the AC actually considered that review a lot. Do you think your method can also address this kind of frequency bias?
No, so it will not address that. So I think that the frequency bias becomes relevant in certain cases, like if you're summarizing opinions. This was with news, and that's not that important for news. we have actually ongoing projects in our lab in which we are addressing that problem. So we are designing summarization modules that take care of frequency bias, because you want the review to be informative of like all sorts of opinion rather than the prominent opinion. In case of news, well, first of all, there aren't that like, the opinions are not that polarized like in reviews, like in hotel reviews. And I think the main idea in news is to just convey the general opinion rather than conveying like fair description. So yes, but we have projects in our lab that address that problem. Okay, so then I'll move on. So the main takeaway from this piece of work was that, first of all, in multi-document summarization, all documents are not equally important. And therefore, unsupervised or supervised, planning of document order is a simple yet effective approach to improving the performance of the summarization module. So, so far we have talked about data to text generation or summarization with auto-generated plans. Basically, the system was self-generating a plan and then basing its output on this auto-generated plan. In the next piece of work, I want to talk about human-provided plans. In particular, I'll talk about story generation with human-provided plans. So this paper was published in EMNLP 20. It's titled Modeling Protagonist Emotions for Emotion-Aware Storytelling. It was led by my student Faiz Ibrahim, who graduated earlier this year. She's now at AI2. So the general problem of story generation is as follows. You are given a title like raw burger, and you want to design a natural language generation system that can generate a short story like this, like the one on the right. Now, there are a lot of methods these days that can do generation like this. Like, you can fine tune GPT-2 or GPT-3, and they are fairly good at what they do. They're not perfect, but at least for short stories, they do a fairly good job of generating a short story. The problem here is that there's no control on the story that is being generated. The system is free to do whatever it wants, and the user has no control. And so even if this generated story is fluent and all of that, it might not be very useful for the user. And so the alternative here is to ask the user to provide a plan for the story. In this case, we define a plan as the emotion arc of the protagonist. So what is an emotion arc? Basically, it's a sequence of emotions tracking the starting, the body, and the ending emotional state of the protagonist. So for example, in this example, the story title is Raw Burger, and the user says that they want the protagonist to feel happy and then angry and then disappointed or sad in the end. So the system here, and this is a real example that was generated by our system. The system generates the story. Tom, which is the protagonist, went to the burger place with his friends. So he's happy here. He ordered a burger. When he got it, he noticed that it was raw. Tom yelled at the waiter for it being raw. So here the protagonist is angry. And then the last sentence stays, he was really disappointed. So here he's sad. So this is the problem statement. You're given the story title, you're given the protagonist's emotion arc, and you want to generate the story which adheres to that title and the arc. So the key challenge here is, how do you track protagonist's emotion? In this work, we explored two possible ways of tracking protagonist's emotion. The first is through Comet. We also use Comet to obtain automatically annotated data, which I'll describe later on. And then we also use emotion classifier. So in the next couple of slides, I'm going to describe these two ways of tracking protagonist's emotion, and then I'll describe our model, which uses these two mechanisms. So the first one is Comet. Basically, Comet is a tool that was developed by folks at UW. And given a sentence like Tom yelled at the waiter, it can give you a lot of inferences about the people in the text. So it refers to the main person as person X. And in this case, I'm highlighting the inference that we are interested in. So Comet can tell you that as a result of this sentence, Tom yelled at the waiter. As a result of this sentence, person X, in this case, Tom, is going to feel angry or upset. And similarly, Comet can also tell you that as a result of this sentence, Tom yelled at the waiter, the other person in the sentence, which is the waiter here, will feel annoyed or angry. So these are the two, like if you're familiar with Comet, then we are interested in tracking the X react inferences and the O react inferences. So this is Comet. This is a very high level description of Comet. We use it as one of the tools to track emotions. The second way of tracking emotion, which we explored, is through a classifier. We basically adapt a pre-trained BERT for multi-level classification over 5 basic emotions. We experiment with anger, joy, sadness, fear, and then neutral emotion. So we are experimenting with 5 of them. And we also do a 2-step fine-tuning process. In the first step, we fine-tune this model on human annotated tweets dataset. And in the second step, we fine-tune it on automatically annotated story corpus. I'm going to describe that in a bit. So these are the 2 ways of tracking protagonist's emotion, through Comet and through emotion classifier. And then now I'm going to describe our method, which uses these 2 ways of tracking emotions to generate the story. So as I mentioned earlier, this is the model overview. The input is the title of the story and the emotion arc, and the output is the story text. We use reinforcement learning for to adhere to the provided plan, the emotion arc, and our base model is GPT-2. So basically, we have 2 rewards to track the protagonist's emotion. One is based on Comet. This variation of the model is called RLEM. And the second way, or the reward to track protagonist emotion, is through the emotion classifier. And that model is called RLCLF. So basically, the RLEM model is using Comet to get the inferences for the protagonist emotions in the generated story. And it describes the reward as the edit distance between the desired sequence of emotions and the generated sequence of emotions. So as you might remember, the desired emotion arc is a sequence of 3 emotions, like in our example, it was happy, angry, and sad. And then there will be some generated emotional reactions that we'll infer using Comet from the generated story. And then we measure the edit distance between these 2 sequences to compute the reward. And then we use reinforcement learning to train GPT-2. So this is our first model. The second model is also similar, except that it uses, it defines another reward that is based on the classifier. So it basically measures the probability of the desired emotion arc for the generated story using an emotion classifier. So it will basically, like if you wanted the first sentence to express happiness, then it will basically measure the probability of happiness for the first sentence. So this is all I had to say about the model architecture. And now I'll describe the data set and the annotation process. So we experimented with the rock story corpus, which has about 100,000 stories about common sense events. Like in this case, I'm showing you a story about someone hiring a babysitter so that they could go on a date with their husband. So as I mentioned earlier, we need annotated data for training our models and for experimentation. And so we annotate the data using this multi-step annotation pipeline. For each story, we follow these 6 steps. In the first step, we identify all character mentions. So I'll read the story. We have 4 people mentioned. So Iris hired a babysitter for her daughter. She planned on going on a date with her husband. Iris waited for the sitter to show. Ultimately, the sitter never showed up. As a result, Iris had to stay home. So in this case, there are 4 people mentioned: Iris, babysitter, Iris's daughter, and Iris's husband. And we identify all mentions of all of these characters in the first step. In the second step, we identify the protagonist. We define the protagonist as the character with most mentions. In this particular case, Iris is the protagonist because she is mentioned most number of times in the story. Then we identify the role that the protagonist is playing in the sentence. So for this, we look at whether the person who we are interested in, the protagonist, is the subject or is the agent or the patient of the main verb of the sentence. We use dependency parse for that. So for every sentence, we know whether the protagonist is an agent or other, where if in case of other, the protagonist is not the main agent. They are patient of the main verb. So once we do that, once we know whether the protagonist is an agent or a patient, we can use Comet to generate emotional reaction. So you need to know whether the protagonist is an agent or a patient because you want to know whether you want to look at X react or O react, like which dimension of Comet you want to look at. But that's technical detail. So once you have identified the person, you can feed every sentence into Comet and get the emotional reaction there. So in this case, we have these emotional reaction. In the fifth step, we wanted to segment the story. So remember, the emotion arc that we expect from the user is basically a sequence of 3 emotions expressing the emotions that will be experienced by the protagonist in the beginning, body, and ending of the story. And so we segment the story following some previous work and get a set of 3 emotions for the story. And then in the last step, we map these emotions into the 5 basic emotions that we are working with, and through the NRC lexicon. So this is our data set annotation pipeline. And once we have the data set annotated, we train our model and then we evaluate it. So I'm going to show you some human evaluation results. So in this case, we are comparing, like through our automatic evaluation, we found that our RL-CLF model was more promising than the RL-EM model. And so in this case, we decided to compare the RL-CLF model with various other baselines, including the RL-EM model. So we are again doing a pairwise comparison. We are asking human judges to read 2 stories. One of them is generated by RL-CLF model, and the other one is generated by the baseline model. And we ask the human to judge the 2 stories based on content quality and emotion faithfulness. We also ask them for an overall judgment, but that's something that I'll talk about in the next slide. So each of these bars, the width of the bar is representing the score, the human provided score for the models. The dark green bar represents the RL-CLF model, and the bar of the other color represents the other baseline. We can see that in all charts, the dark green bar is wider, which indicates that the RL-CLF model got a better score than the baseline models. So I mentioned that we asked human judges to judge the stories based on content quality and emotional faithfulness. And then we also asked them to consider both of these factors simultaneously and choose one of the 2 in stories that was being showed to them. And here are the results of that experiment. So in this experiment, each bar is representing comparison of RL-CLF with a baseline. The name of the baseline is at the bottom. And the length of the bar is 100. The orange part of the bar is indicating how frequently the human judges chose the RL-CLF model or the output of the RL-CLF CLF model over the baseline model. The blue bar is representing how many times human judges preferred the other model, the baseline model, over the RLCLF model. And then the gray bar, part of the bar represents ties. So basically, we can see that in all cases, the orange part of the bar is taller than the blue part, which indicates that the human judges preferred RLCLF over the baseline more frequently than the other way around. And so this indicates that RLCLF model is producing better output than the baseline. I also want to quickly show you some sample stories. So the input here is the title, which is dance in this case, and the user provided these two possible arcs. One is fear, joy, joy, and the other one is sadness, joy, joy. And you can take a look. I'll give you a moment to like read the stories. Basically, what I'm trying to illustrate here is that how we, by providing the emotion arc, the user can control what's going to happen in the story, how the story unfolds. I'll just stop for a moment so that you can read. So again, these are like stories generated by our RLCLF model. So to conclude, in this piece of work, we propose two emotion consistency rewards that help the story generation model in adhering to the desired emotion arc without sacrificing story quality. And we showed that how user-assisted planning can help in controlling the content of the generated stories and helps lead to probably more useful stories. Are there any quick questions? Or if you want, you can just wait till the end because I'm almost done. Okay, I'll just wrap up. So to conclude, I talked about these three pieces of work. In the first two pieces of work, I showed how a generation or a summarization model can do better if it can work with auto-generated plans. And in the third piece of work, I described how human-provided plans can help in better automatically generated stories. But this is like a very small part of what's going on in our lab. And I want to quickly mention what other exciting stuff is going on. So one interesting thread going on in our lab is on fairness in natural language processing. So for example, we had a paper in EMNLP last year where we were removing demographic information from text classification for text classification. So basically, the idea here is that text representations, like representations of tweets, so they encode demographic information of the author. So for text written by women are different than text written by men. And so their representations are also different. And so when these representations are used for any sort of classification like sentiment classification, they end up relying on demographic information, which is undesirable. So we presented a method that could remove or adversarially scrub demographic information from text representations with the goal of doing classification. And then in another piece of work, which got accepted to tackle recently, we showed that even if you don't have a target task like text classification at hand, you can still use our method to remove any kind of demographic information from text representations. And then you can use this representation for whatever task you care about. Another thread of work in our lab on summarization. In particular, we have worked quite a bit and we are working on low resource summarization, in particular opinion summarization, so weakly supervised or unsupervised opinion summarization. And then The last thread is on narrative understanding and generation. We have a bunch of papers on narrative generation, including in interactive story generation. And also we have released data sets on narrative understanding. And these ideas are applicable not just to stories, but to general text. So for example, in the paper that was published in EMNLP last year, Is Everything in Order? We measure coherence of text and how to unshuffle a given piece of text so that it becomes coherent. So that's all I wanted to say. I hope I gave you a good overview of what's happening in our lab, and I'm happy to take any questions.
Yeah, thanks, Snigdha. This talk is very exciting, and those works are excellent. I think we already have one question from the chat by Nan. So can we use Comet to do automatic evaluation? I think that's probably a question about the third part of the talk.
Yes, so actually I did not include all the results here. We did some automatic evaluation. So we had automatic evaluation for content quality, like using the standard measures, perplexity, blue, and all of that. But we also used Comet for emotion faithfulness. There is a conflict of interest there in using Comet itself for evaluation. But anyway, automatic evaluations are not like the final evaluation. And so this gave us an idea of like relative performance of models. And then we used human evaluation to actually do the final evaluation. But yes, we used that for automatic evaluation. That's how we decided to compare against RLCLF model in when we were doing human evaluation.
Thanks. And I think Jay is raising his hand.
Yeah, I think that that was a great talk. Thanks for giving it. I had a couple of questions. Question number one, you started the talk and you mentioned this, babies think before they speak. So do you have any other thoughts on kind of the human biases in ordering and how we tell stories, how we understand stories? I mean, that planning component, it seems more kind of from a machine perspective, but have you really done any kind of surveys of how humans tell stories and what their cognitive kind of reward functions are, so to speak?
So we don't have, I think we don't have that kind of expertise to do that. But we have been talking to experts in narratives, like we have been talking to a screenwriter actually to understand how people who write stories for a living, how they write stories. And we have learned quite a bit. And in fact, so this is a screenwriter from the Indian film industry that we have been in touch with. And one thing he pointed out is that a lot of these stories, they build up on stereotypes. And taking that cue, we actually had a paper, and I'm forgetting the venue off the top of my head. Actually, it's here. Yeah, it was in EMNLP last year, where we were looking at how there is implicit gender bias in stories, and they are there in machine-generated stories, and that gets sort of amplified in human machine-generated stories. So we were looking at how men and women are portrayed differently in machine-generated and human-written stories, and how their emotional experience is different. We also looked at, the third factor we looked at was how their motivations are different. So like men are mostly motivated by, power and money. Women are motivated by looking beautiful and attractive. And the interesting bit there was like, you of course see that in movies and stuff, but we experimented with rock stories, which were sort of which were again human written, but the humans were instructed to write like common sense events, like everyday events. They were not instructed to write a bestseller, but just something that comes to their mind. Like there are stories about going to the beach or fixing something or cooking something, like everyday events. And there also you see these biases, which indicates like how embedded these biases are in human minds, and that gets amplified in when you use machines to generate stories.
Yeah, it's really interesting, and yeah, that sort of stereotype connects to all the AI ethics stuff. One more question. I mean, I guess to share, we did some work on the same sort of narrative understanding, but in the context of fables, like Aesop's fables. And if you're familiar with them, they have a moral. And what we found is it's really, really hard. You know, we actually had a similar kind of emotional arc alignment to find analogical stories, but that's not really good at finding two stories which might have very different surface forms, but the same moral. But it's a different type of common sense structure, cause effect structure, et cetera. Do you have any thoughts on getting deeper than just emotions? Because emotions seem like the simplest layer that you could look at, and deeper in the semantic space, I think, is a lot harder. And it sounds like you're thinking in that direction. So any advice for us, or any thoughts on that problem?
Well, I don't have a solution, because if I had a solution, I would have another paper that we are working on currently. So in this project that we are working on, this is in collaboration with other people at UNC. We are working on a related problem. There is a very short story, and then there is a, what do you call it? A quote for it, like, early bird gets its worm, or something like that, or a bird in hand is better than two in bush. And it's like moral in the sense that you don't necessarily see a bird in the story, but when you do the mapping, that's what the underlying message is. And yeah, we are struggling with it because, and we are trying to solve, like, there are a bunch of problems here. Like the simplest one is, if you are given a story, can you pick one of the quotes for that story? And we are facing problems there because, of course, there is no lexical overlap between the quote and the story. And we are trying to get some sort of representation that goes beyond like lexical stuff. It tries to map what's going on at like an underlying level, the skeleton level of the story. We haven't been very successful so far. But yeah, I think the problem that you are working on is very closely related to what we are doing. I think
I'll share what we have. I think we have a workshop paper on it, and maybe there's some collaboration opportunity. But
yeah,
it's good
happy to talk about it, because it sounds like the underlying problem is the same.
Yeah. Okay. Thanks.
Okay, I think we are at 12 p.m. already, so that can conclude this seminar. So thanks once again for Snigdha to giving this very exciting talk, and hope to have more discussions and also follow up potential collaborations with you.
Yeah, thanks for inviting me, and I really enjoyed the questions. And please feel free to ping me if you have any further questions or clarifications, or if you want to discuss anything further. Thanks for joining. Bye.
Bye.